Hello everyone, let's continue with chapter 8. So, we've talked about now the shell model up to potassium. Now we can see many of the trends in the ionization energy are now reflected in the structure of our periodic table. So we talked about that last time, how the structure of the periodic table is separated into these sub-levels. So the energy levels are arranged into sub-levels. So if there's only a principal energy level and all the orbitals were the same, we wouldn't have the periodic table separated as it is today. So the fact that it's adopted and structured in such a way kind of reflects on the atomic structure. Okay, so one of the things we can look back on are that there are two elements in the first row of the periodic table, and that 2 electrons fill the first shell. Now there are 8 electrons in the second and third shells, and 8 elements in the second and third rows. In the second and third rows of the periodic table. So that all checks out, right? Okay. All right, let's check this checkpoint. Is the radius of the valence shell of sodium larger, smaller, or the same as the radius of the valence shell of lithium? Okay. So this might be kind of confusing to think about since we haven't talked about atomic radius of elements yet. We'll be talking about that in the next series of slides. So let's think about this. So sodium has 3 shells, right? So sodium. Right? Whereas lithium only has 2. Okay? So if we think about the ionization energies, it kind of tell us like which one has a smaller or larger radius. So the first ionization energy, so the first okay, so the first ionization energy of sodium is much less than the first. First ionization energy of lithium. So by this analogy, we can conclude that the radius of sodium must be larger because the valence electron is in a shell that is further away from the nucleus, therefore requires less energy to remove that electron to form an ion. So that's how we can kind of conclude that the electron is further away from the nucleus, and thus sodium has a larger radius of radius than lithium. Okay, so now we're going to talk about the physical evidence for the arrangement of these energy levels. Okay, then we have to delve into something we call photoelectron spectroscopy and the structure of atoms. Okay, so one question we might have are, for atoms with so many electrons, do all the electrons in a given shell have the same energy? So do the 2s and 2p energy levels, do they have the same energy? And we can answer that question. So right now we just know that as you add more electrons into the shell, you're going to increase the ionization energy if you go across the period, right? Okay. So we can answer this question. We can answer this kind of problem by using a slightly different technique. Instead of ionizing the loosely held electron, we can measure the energy required to remove any electron from a neutral atom in the gas phase to form a positively charged ion. So how this works is it's much related to the photoelectric effect proposed by Albert Einstein. So this time, radiation will be shined on the sample, and will give it enough energy to excite in the atom to the point, that an electron can be ejected from any shell. So it doesn't have to be the valence shell. It could be from the inner shell, or the lowest energy level, the second lowest energy level. So it can be from any energy level, and we can get information about the energy it takes to remove all these electrons, and we can answer the question: Are all the electrons in the same energy level? Do they have the same energy? So that's a pretty useful piece of information, and it kind of supports our arrangement of the periodic table. Okay, so here's a little diagram of a setup for this kind of spectroscopy or experiment. So what happens is that your atoms you have an atom source, and it will be radiated with photons from X-ray or UV light. Okay, so what happens is that the energy of this photon is going to be much larger than the ionization energy of the atom. So what happens is you're going to have some excess energy that form the electron, and that causes the electrons to move. It causes when the electron moves, it will carry excess energy in the form of kinetic energy, and so the energy required to remove this electron from the atom will be the difference between the energy of radiation absorbed by the atom, Hb, and the kinetic energy of the ejected photoelectron, so the electron that absorbed light. Okay, and we have this equation to kind of calculate the ionization energy that's required to remove that electron. So you see in this pictogram here, you can either eject a core electron, or so we denoted Ke subscript I. That means inner electron. So we ejected an electron from the inner shell. And then for outer shell, we can determine the ionization energy for the outermost electron, or as we know it, ionization energy. Okay. So since the energy of the inner electron will be higher, it requires more energy. So it'll require a larger amount of energy to remove that electron versus an outer shell electron, and is as we see here in the second kind of diagram in this picture. Okay, so that's how we kind of determine the energies of these electrons. Okay, so now we're going to be talking about some spectra here. So you may see a spectra like this similar on the homework. So for the homework, refer back to these lecture slides and to talk about this for the homework. Okay, so photoelectron spectroscopy, it differs from ionization energy because it can remove any electron from any shell. So So we obtain data as so in any kind of spectroscopy, you're going to see some peaks like on a graph. So there are peaks in the spectrum, and they plot the intensity of the absorbed signal on the vertical axis and the energy that we need to inject an electron on the horizontal axis. So the main difference is on this spectra, instead of starting from left to right, you increase from right to left. So that's the only difference. Like in the normal graph, we would start from 0 to increasing numbers from left to right, but it's the reverse here. Okay. All right. So we plot it. So it shows that the increasing energy. We plot it this way to show that the inner electrons require more energy, and it's kind of situated on the left since you're going from inner energy to higher energy on the right. So it's kind of counterintuitive, okay? And one thing we also need to recognize is the height of the peak is directly proportional to the number of electrons of equivalent energy ejected during the experiment. So what that means is that if the height of the peak is higher, that means there can be more than one electron can occupy a specific energy level or sublevel. So that's useful information. So if we see two peaks, for example, and we have a ratio of 2 to 1, we can say one of the energy levels from which the electrons are removed in this experiment contain twice as many electrons as the other. So that kind of says, okay, if we have two different energies, they must be in two different orbitals. Okay. So here is the first 5 elements, and they're simulated photoelectron spectra. So we kind of simulate them so the graphs kind of look a bit neater to illustrate our concept. So in an experiment, they won't necessarily look like this perfect. So that's something to watch out. If you ever read papers and go to scientific research, look after spectra. How is it? Is it absolutely perfect? Are all the peaks symmetrical? That's not really how things work. Sometimes it does if you get really good spectra, but most of the time the spectra you get, they're not going to be perfect. Okay, so that's just how research is. Okay, all right. So we see here from hydrogen, you only have one peak because in hydrogen you only have one electron. In helium, we see almost twice the amount of peak, twice the size of the height of that peak. And we see here that it takes more energy to remove those electrons, and that makes sense, right? Because the number of protons on helium is double that of hydrogen. And we see here that the height is doubled, and that makes sense because now helium has twice as many electrons in the s orbital. Now, when we go from lithium, we see two peaks. So we see a peak of the same kind of height for the peak in helium, so that represents the s orbital electrons. And then we see a peak further along the way that's of much lower energy. Okay, so 0.52. So that represents, so when we get to lithium, we're now in the second energy level. But remember, in the second energy level, we have S and P. So this kind of demonstrates that the P and S orbitals, they are of different energies. Okay, and then eventually we get into no. So what I meant to say, lithium has a 1s orbital and a 2s, right? So that kind of shows here that we have not only the 1s showing up, but the 2s. So there are different energy levels, so that's why they have different energies. And then when we go to beryllium, now we occupy all of the 2s, so that's why the peak intensity there increases to 2 compared to lithium. And then when we get the boron, we have the 1s filled, the 2s filled, and then eventually we get into the p orbital, and that's why you see an additional peak of higher energy, and that shows you that the p orbital and s orbital are of different energies in the same sublevel. Okay? All right. So, what factor determines the number of peaks in the photoelectron spectrum? Let's go over that. Okay. So the number of peaks in a photoelectronic spectrum is determined by the number of different energies that the electrons in an atom have. So the number of peaks in the photoelectron spectrum is determined by the number of different energies that electrons in an atom has. So, for example, so for boron, you have electrons in the 1s, the 2s, and the 2p. So you should have three different peaks for the different type of electrons and energy levels. So that's how you would answer that question. Okay. So now let's go into electron configurations from photoelectron spectroscopy. So let's go over the first 5 elements from their PES spectra. So hydrogen only has 1 peak, only has an electron. Helium has 1 peak, and it's shifted to the left, and the hydrogen peak is double that for hydrogen because there's 2 electrons in helium, and they occupy the n equals 1 shell, and since it's a higher atomic number, it's going to have a higher nuclear charge. Lithium, we expect 2 different peaks, one for the 1s, and then the second one for the 2s, or the second energy level, and that's what we observed. So the valence electron is easier to remove than the 2 electrons in the n equals 1 shell because they're closer to the nucleus, right? Beryllium, there are 2 peaks observed with intensity of equal intensity, and this makes sense because beryllium has both the 1s and 2s orbitals filled. So it has 2 electrons in the n equals 1 shell and 2 electrons in the n equals 2 shell. So that makes sense there. So boron, we see an interesting case. We see 3 peaks. There's a peak corresponding to removing electrons from the 1 shell, but 2 different peaks in the n equals 2 shell. And then if we compare the value of the ease of the electron to remove in each of these elements, it matches up with the first ionization energy that we saw previously in the previous lecture. Okay, so that makes a lot of sense. So that's pretty cool. Okay. So let's answer this question, and then we'll stop the video here and pick up in the next one, okay? So why is there only 1 peak in the photoelectron spectrum of helium, even though there are 2 electrons in the helium atom? So that's a good question. So there is only 1 peak in the Photoelectron Spectroscopy spectrum. because maybe I should write helium so people don't get confused with the word he. Because both of its electrons so remember there's only one s orbital, right? So if both two electrons are in the same s orbital, they have the same energy. So because both of its electrons have the same energy, so that's something we should think about. So all s orbitals, so no matter what orbital an electron is in, especially if it's in the p shell or d shell, no matter the orbital, they'll have the same energy because all the orbitals are what we call degenerate, or that means they have the same energy. Okay? Because both of its electrons have the same energy. The same energy here. Okay? Alright, so let's stop there and we'll pick up in the next video. I'll see everyone then.